International years are usually approved by the United Nations, and UNESCO is the implementing body within the. And ICTP is actually governed by a tripartite agreement between UNESCO, the International Atomic Energy Agency, and the Italian government. So we are actually playing an important role in the International Year of Quantum. We are on the steering committee, ICTP. And the purpose of this International Year of Quantum is to have a broader awareness about the importance of quantum in the years to come, both for technology and for science, and to get the relevant leaders in the field or the stakeholders collaborate and figure out the policy and strategy for the future. So from that point of view, I think it's a very important year which gives us an opportunity to engage with the global community for this very important subject. Like in any science, international collaboration is of fundamental importance because science actually does not respect national boundaries. Even if you go back to the history of science, sometimes even when, for example, in Europe, when the countries were at wars with each other, some breakthroughs even in quantum mechanics came from France, some came from Germany, some come from the United Kingdom. And the scientific thought does not respect the current geographical or political constraints. So, for example, famously, de Broglie was French, Heisenberg was German, Dirac was British. So, this is really ingrained in the way science is done. And that's why Salam had conceived of ICTP as an international hub for science. And that's also why I find directing this center a particular honor, not only because of the quality of science, but also this role it plays in internationalization of science. And so ICTP therefore has a natural role to play in any such international event. In fact, we had a very high-level event in May this year. We had some 10 Nobel laureates coming to ICTP who had made pioneering contribution to the new quantum, if you like, the second quantum revolution, which has to do with the quantum information and so on. Because ICTP's fundamental mission is open science, it makes complete sense for ICTP to play this role. Of course, ICTP, usually the way we function is that we have some 6,000 scientists coming to visit our campus. And they come from all parts of the world. And you can often see a leading scientist and Nobel laureate talking to a young beginning student. This is the kind of thing that can happen only at ICTP. And this role is equally important. So this is in general, we do this, not only specifically for the quantum. But with this new strategic plan, in 2025, because we celebrated the 60th year last year, I had formulated the new strategic plan of ICTP for the next 60 years, in a way, as a beginning for the next 60 years. And we have three main priorities. And one of the priorities is International Science Alliance, is to build an alliance with scientists. This is very similar to what Salam had in mind, but implemented somewhat differently than in his time. What Salam was doing in the 60s is not the model that we can adopt in the 21st century. I would look at it more as equal partnerships rather than ICTP just being one-way traffic, I think now it is more of an equal partnership because countries like, let's say, China or India or Brazil, the BRICS countries are certainly at a different level of their development, both economically and also scientifically. And also countries like Pakistan have come a very long way from where they were in the 60s. So we actually want to engage uh, with them on a more equal footing. And I have been discussing it with several governmental agencies in different countries who signed agreements with the Brazilian ministry, for example, with India. Pakistan actually used to give us we had an agreement with Pakistan for a very long time, and I think it continues today, which allows us to welcome a good number of Pakistani scientists to ICTP, where ICTP picks up part of the burden of the financial burden, but also the Pakistani government is happy to support it because it helps their scientific community. So second initiative is the International Consortium for Scientific Computing, which is particularly relevant for computing related matters, which includes quantum computing, which is sort of we are still not there, but it's sort of the wave that is coming maybe in the 15 years from now. I work in sort of particle physics, fundamental physics, black holes, rather like Salam, in the same stream, unification, which is a bit not exact. It's quite far from some of these quantum technologies that are developing. And I, of course, know the basic parameters, and then I have reasonable familiarity. So therefore, I'm speaking now more as a director rather than as an expert in this field. I would say that, there is, of course, big promise. There's a big quantum promise. One way to understand it is that quantum mechanics has two very counterintuitive and very surprising aspects. One is that energy is quantized, energy is quantum. This goes back to Planck, that energy, a photon, it comes in lumps of energy. You don't get just a continuous energy coming from a light wave. It comes in lumps. Electron is, of course, a lump of energy. So, but everything in the world comes in lumps of energy. So energy is quantized, which also means that there are energy levels that are discrete. And this fact is fundamental to the first quantum revolution, both scientifically but also technologically, because all the semiconductor industry will depend on the fact that there is a gap in the energy. And you have to do all this doping, and everything that you do with semiconductors depends on the fact that the energy is quantum. What is being explored now? So therefore, that has already had a huge impact. The entire semiconductors, even our conversation that is happening, which depends on all the semiconductor breakthroughs in semiconductor technology, transistors, lasers. This all comes from the fact that the energy is quantum. What is going to be the important thing next, which is even more subtle aspect of quantum mechanics, is that information is quantum. Because a classical information is stored in terms of ones and zeros, up, on or off. But it's a very peculiar property of quantum mechanics that you can have what is known as the linear superposition. You can have some fraction of it is being 1 and some fraction of it is being 0. And there is also this phenomenon of quantum entanglement, that things which are very far away from each other could nevertheless be correlated with each other in a very non-trivial way. And this is harder to explain in common terminology, because it's really the most counterintuitive aspect of quantum mechanics. But that's the aspect that is being harnessed in quantum computing. And so I think there is a big promise. There is a big quantum promise on this front in the coming 100 years. But there is also a quantum hype, I would say, that there is always companies want to exaggerate some of their claims. So one has to, similar thing is happening also with AI. I think one has to keep your eyes open to what is coming, but not get too carried away by some of the exaggerated claims. I would say that, I'm speaking as an outsider. I'm not very closely familiar with the details of the science there. But I think there are areas like quantum metrology, which are clearly going to be very important. They're already, when quantum simulations is something that can happen very in the coming future. For example, you can simulate some Hamiltonian, some drug, let's say, using qubits, and you can learn about how that particular drug behaves in a much faster way. These kinds of applications of quantum, quantum computing, or more like quantum simulations, it's like an analog versus digital version of quantum computing, and that I think is already becoming possible. Whether or not you can get programmable, general purpose quantum computer, I would say that the jury is still out, and some people are very enthusiastic about it, but also some of the experts that I have talked to are cautiously optimistic and have reservations about the. So I think one should keep the mind open, but not get carried away, is what I would say. And there are areas where you can actually sort of step in without necessarily committing yourself to something which may be not so near in the future. Taking this away from the quantum technologies, more towards the theoretical aspects of quantum information. And black holes are a fascinating laboratory for understanding the implications of quantum information theory. For example, Hawking's famous result seems to indicate that information is lost. And quantum mechanics doesn't allow this. In quantum mechanics, information can never be lost because it's the time evolution in any quantum system is always unitary. Unitary means that it's U dagger U is equal to 1. And okay, I'm talking some technical terms here, but therefore information is not lost. For a black hole, apparently Hawking showed that if you throw in information into black hole, what comes out is thermal. And it seems to forget about whether you threw in Encyclopedia Britannica Volume 1 or Volume 2, what is coming out would look the same. It looks thermal. So it looks like you have lost the information. Whether it was Volume 1 or Volume 2, you cannot read it from looking at the radiation that is coming out. Even if you throw something in the sun, you might think that something similar happens, but actually not. If you are very diligent in theoretically looking at what is coming out of the radiation of the sun, and if you really keep track of everything that is coming out, you can actually read whether it was Volume 1 or it was Volume 2 that fell in. But you cannot do that for a black hole because of some very specific causal structure of a black hole. This paradox has led to very fascinating investigations, and I have also thought about it a lot. And it has led to this notion of holography, that the information of a black hole, normally the information qubits in a room, let's say, the number of qubits you can place in a room is proportional to the volume of the room. What you find is that the number of qubits you can place on a black hole is proportional to the area of the surface of the black hole. So it's like a hologram. All the information about the inside of the black hole stored on what is on the surface of the black hole. And this has been formulated in a very precise way in what is known as the ADS-CFT correspondings. And there are some very fascinating connections between quantum information theory on one hand and theory of gravity on the other hand. And this is a very interesting area of research. It's very theoretical in that I'm not sure that it will have not necessarily a bearing upon directly on the quantum technologies, but it has been very suggestive in some ways, and it has been, many quantum information theorists have been interested in this and vice versa. I think it's a fascinating field of research purely at a theoretical level, and maybe its application will happen 50 years from now. It's great to be excited about this because these are really fascinating areas of scientific research. As I said, it can go in many different directions. You could go in the direction of quantum technologies, you could go in the direction of simulations, or you could go in the direction of information and gravity, as I said. So it's a very fertile ground, and now experiments are happening. Some of the very subtle, for example, Bell's inequality, which was a very subtle aspect of quantum mechanics, which was thought about, going back to the EPR, Einstein Podolsky-Rosen paradox, going back several decades, people have been able to actually measure it in the lab. You can prove that Bell's inequality is how does a quantum system or a process, a classical system, the Bell's inequality is actually quantum mechanics violates it. So these measurements can be done now, and Nobel Prizes have been given for it. It's a really exciting time, both at the experimental side, and that's one area. It's of course very difficult for a developing country like Pakistan, or also for a country like India, which has a bigger scientific community, to make huge investments, because it requires, but at the same time, I would say many of these experiments are relatively cheap. I mean, it's not like a huge accelerator, like the CERN accelerator. Some of them are tabletop experiments. So I think it makes sense to invest in some of the experimental side of this very exciting field. But of course, these are questions of national priorities, and one has to think it through. I think I'm sure Pakistan has a quantum strategic mission. I know that India has one, and they plan to invest quite substantially in this field. And thinking of International Center for Theoretical Physics, as founded by Salam, was that compared to that, theory is cheap. Theorists just need a paper and pencil and maybe a computer. So that's one way you can have some bright young scientists who can work on the theoretical aspects without necessarily having huge national investments. And ICTP is surely happy to play its role. If she can, I would look forward to strengthening. I would look forward to actually maybe visit Pakistan to strengthen our collaboration. There is a strong legacy going back to Salam. So it makes sense for the government of Pakistan to think about. And ICTP has welcomed hundreds of, maybe 1,000 Pakistani scientists in the past, and we can probably do more in the coming years if there is interest and willingness from the side of the government or the national agencies or universities. You already have some collaborations with some of the universities like LUM. So we would be very happy to play our role in this context of International Science Alliance, so that global collaboration can happen. There is private initiative and private investment in this exciting field. So I would encourage them, and I would congratulate them for taking this effort. And I think it's really important that you interact with some of the experts in the world globally, so that the mission of the center is properly on track, and you don't get. I think in this field it's easy to get distracted in some wrong direction, because it's a very young field, and for example, different companies are pursuing different platforms. Somebody is doing, trapped ions, somebody is doing superconducting qubits, and there is no settled agreement on which is the best. It's not like the transistor where it was clear that you do silicon or whatever, gallium arsenide. Technology there was a quick agreement about what technology is going to be most fruitful. This is not yet the case in quantum technologies. So one has to therefore tread cautiously, but not. But it's good that it's important that you have to get engaged and understand where are the opportunities. This is also therefore exciting time because there are frontiers are opening up. So one has to approach it like that. I think it dovetails nicely with what I was saying, that relatively quantum simulators is something that is, in a way, low-hanging fruit in this business, as I would say, meaning where you can actually start doing something useful without solving all the problems of coherence, decoherence, and whatever error correction. So, yeah, so I would say well done, and I hope the Pakistani community continues on this path. I hope that I can visit Pakistan one of these days. I had an opportunity once, but something happened and I didn't end up going. But I think we do have collaborations with the Pakistani scientists, and for example, lumps people have visited ICTP. So I would be very happy if there are ways to strengthen the collaboration with Pakistani community of scientists.